Hi, I'm Tom Beebekauser with Wetland Restoration and Training. In this episode, we're going to be looking at how wetlands, streams, and rivers can be restored from constructed impoundments. The place where we're working is called the Hunting Grounds, and it's located on the Yaqan Nukiy First Nations Lower Kootenay Band Reserve Land near Creston in British Columbia, Canada. And we're going to be working with Norman Allard Jr., a community planner with the Lower Kootenay Band. I started working with Norm over 8 years ago to restore wetlands, streams, and rivers from constructed impoundments. This is an exciting project with unbelievable accomplishments, and let's get started. The Hunting Grounds Impoundment was constructed by Ducks Unlimited Canada on the Yaqan Nukiy First Nations Reserve near Creston, British Columbia. The 517-acre impoundment was a failure because it did not hold water even when water was pumped in constantly from the Kootenay River. Episode 21, Impoundment Construction and Management, describes in detail why the Hunting Grounds Impoundment didn't hold water and how the construction of the impoundment destroyed hundreds of hectares of natural wetlands along with streams and rivers. The vegetation on the hunting grounds is dominated by dense reed canary grass. Reed canary grass grows thick and tall in drained wetland basins, and it crowds out native species of grasses, sedges, trees, and shrubs. The Yaqan Nukiy worked in partnership with the British Columbia Wildlife Federation, Columbia Basin Trust, and the Fish and Wildlife Compensation Program to restore wetlands and streams within the Hunting Grounds Impoundment. One of the main objectives of the project was to return natural flooding to the hunting grounds that had been cut off by the construction of dams for the impoundment. Before the Hunting Grounds Impoundment was built, flooding from the Goat River and the Kootenay rivers would annually fill the natural wetlands with water, and this would provide habitat for a diversity of species, including the bald eagle, osprey, mallard, white sturgeon, and burbot. We decided to remove all the dams that had been built for the impoundment to reconnect the hunting grounds with floodwater from the rivers. An important step prior to construction was to determine at which elevation to remove the dams. This was more complicated than it sounds. Before the impoundment was built, the banks of the Goat River and the Kootenay River served as low dams with gradual slopes to retain floodwater in the hunting grounds. When there was a flood, water would flow over the riverbanks in low places that we call inlets. It would enter the hunting grounds and fill the natural wetland basins on the floodplain. When the floodwater receded, most of the water would drain out of the hunting grounds in what we call outlets. However, water would be left behind in the wetland basins. This drawing shows how the dam constructed for the impoundment was blocking floodwater from entering the hunting grounds and filling the wetlands. This drawing shows floodwater rarely entering the hunting grounds because the dam is only partially lowered. This drawing shows what we would like to see happen every spring when the Goat River floods. The constructed dam has been removed and the riverbank has been shaped so that floodwater can enter the hunting grounds and inundate the restored wetlands. You can see where the restored riverbank is high enough so that when floodwater recedes, water will remain in the wetland basins. This drawing shows where a dam was breached at the location of the water control structure. The rest of the dam was not lowered or removed. Floodwater has entered the impoundment through the breach in the dam. However, the floodwater that entered the impoundment through the breach will leave the impoundment just as quickly because the impoundment basin contains ditches and is sloped to drain towards the water control structure just like a bathtub. Restored wetlands that are annually inundated by floodwaters can be expected to be perennial, while wetlands that are not inundated each year will be ephemeral. Before we could determine what elevation to lower the dam to, we had to identify the elevation that floodwater would enter the hunting grounds each spring. Here, Norm Allard uses a GNSS unit to determine the elevation of the historic inlet that once allowed floodwater to enter the hunting grounds. Norm Allard identified that prior to impoundment construction, floodwater entered the hunting grounds along the eastern edge along an outside bend in the Goat River. Ducks Unlimited Canada blocked this inlet by digging a major ditch to cut off the bend in the Goat River and then built a dam to block floodwater, drying out the hunting grounds. The dashed red line shows the center of the dam that was built to prevent the Goat River from flooding the hunting grounds. The dam was difficult to find with its great width and gradual slopes. The presence of Canadian thistle shows that the site was disturbed to build a dam. This photo shows the natural bend in the Goat River that was dried by the major diversion ditch. The Goat River was diverted so that floodwater would not flow into the hunting grounds. Norm identified flood elevations for the Goat River using data from river gauging stations, but more importantly, from observing the elevation of the drift line of vegetation and large woody debris that settled on the side of the dams when the floodwater receded. Norm determined that the elevation of the inlet to the restored hunting grounds should be 25 centimeters higher than the normal elevation of water in the cutoff channel of the Goat River. The Goat River would enter the hunting grounds at this location when the elevation of water in the cutoff channel increased by 25 centimeters. The constructed inlet stream would flow into the hunting grounds by following streams that had also been drained with ditches. We tied colored plastic flagging onto vegetation to show the excavator operators the center of the inlet stream to build. Here, Ted Crane, the excavator operator, is digging the inlet stream channel through the dam that was built to prevent floodwater from the Goat River from entering the hunting grounds. Ted starts by digging the center of the stream channel 2 buckets wide. I'm checking elevations often to make sure that the stream is built to be level in length and in cross-section. Ted will return to widen the stream channel and to shape gradual banks after digging the center of the channel on grade. The center of the inlet stream is dug first. The path of the stream is made level so there won't be any erosion. The excavator widens the stream channel and makes it level in cross-section. The dozer operator spreads the soil that is removed from digging the stream. We guide the dozer operator so that the soil is not placed in wetlands that we're also planning to restore. You'll notice that only one side of the stream is being built at a time. The stream channel is built wide and level in length and in cross-section. It has gradual sloping banks, so there will be a sheet flow of water and no erosion. The soil that was used to build a dam across the inlet when the impoundment was built is brown in color. The gray-colored soil is from a wetland that was filled when the dam was built. Gravel was uncovered during construction of the inlet. This gravel was brought in years ago so that trucks transporting soil to build the impoundment dam would not get stuck driving across the drained and the filled wetlands. Here the excavator operator is shaping a gradual bank on one side of the stream. The width and shape of the stream was made to match the natural stream channels that had been cut off by the construction of the impoundment dam. The excavator operator spreads loose soil with scattered clumps of vegetation over the graded stream bed to provide for plant germination and growth. We're not using the rough and loosen technique in this restored inlet stream channel. This is because there could be erosion over a rough surface when there's a strong flow of water that enters the hunting grounds. Norm Allard surveys what will be the primary source of water for the restored hunting grounds. The Goat River will now inundate the hunting grounds when the elevation of the river rises only 25 centimeters. Sedges and cottonwood trees are growing in the restored inlet stream 1 year after construction. There is no erosion because the stream channel was built wide and level with low sloping banks. Outlets are streams that carry water back into the river when the floodwater is receding. We examined historic aerial photos and searched the perimeter of the hunting grounds to identify where natural outlets were located before the impoundment was built. We also identified where new outlets could be built that would carry floodwater out of the hunting grounds and over a gradual slope and not cause erosion. We determined that the elevation of the outlet should be 10 centimeters lower than the inlet after measuring elevations within drained wetlands on the hunting grounds and by observing the elevation at which large woody debris had settled along the base of the dams. For wetlands to contain water after flooding, their basins must be lower in elevation than the outlet. In addition, there must be pathways for floodwater to flow into the restored wetlands that are at the same or lower elevation than the inlet. The dashed blue line shows the location of the natural outlet that was filled and blocked by the construction of the impoundment dam. Large boulders were placed in the outlet, most likely to control erosion during construction of the impoundment. The elevation of water in the Goat River South was historically much higher, being equal to where the willows are growing. The elevation of water in the Goat River South has dropped significantly because of the head cuts caused by the shortening of the Goat River in the 1930s and from the ditching and the diversion of the Goat River South for the construction of the impoundment. To restore floodwater access to a floodplain, one should avoid breaching a dam where the impoundment drain pipe is located. If the dam is breached at the location of the drain pipe, major head cuts will form, and these will advance into the drained impoundment. Another huge problem with only breaching the dam is that floodwater will drain out of the impoundment as fast as it comes in. The primary outlet for the hunting grounds would be a stream that would carry floodwater over a gradual slope and not cause erosion. The entrance to the outlet was set only 10 centimeters lower than the inlet. The secondary outlet for the hunting grounds would be in a valley that would carry an overflow down a steeper slope. We plan to armor the slope with rocks to prevent head cuts from forming. The elevation of the secondary outlet was also set to be 10 centimeters lower than the inlet so that floodwater would not drain out of the restored wetlands. The excavator begins construction of the outlet by removing reed canary grass growing in the path of the stream being built. The colored plastic ribbons show the operator the location and the width of the stream to be built. The excavator is now digging a trench that will be the center of the outlet stream. The bottom of the trench is being dug on a gradual slope of only 0.5%. The elevation of the outlet is critical to the success of the project. If set too low, the outlet will act like a ditch to quickly drain water from the restored wetlands and streams that are on the floodplain. The narrow trench is widened so that water may flow over the outlet in a sheet-like pattern. The stream channel and floodplain are combined into a wide swale with gradual slopes. Here the excavator operator widens and shapes gradual slopes on the banks of the outlet stream, while the dozer operator backs up and spreads the soil removed from digging the stream. This soil is spread in a thin layer away from the stream. To control erosion and to prevent head cuts from forming, we used rocks to armor the steep slope where the outlet stream flows over the bank into the Goat River South. The excavator scoops up a bucket of rocks that were delivered by the dump truck and then carries these rocks over to the stream channel where they are placed high up on the stream banks to control the erosion. The rocks vary from 15 to 30 centimeters in diameter. They are angular in shape, so they can be wedged tightly together. Rocks are used to armor the entire width of the stream being built, where the slope exceeds 0.5% to control erosion. The excavator operator uses a bucket of the machine to push the rocks into the ground and to fill spaces between the larger rocks. The orange wire flag is placed in the ground where the channel is at the correct elevation prior to the placement of the rocks. The elevation of the Goat River South is much lower than it was historically, explaining why there is a steep slope leading down to the water in the Goat River South. Here's how the rock-armored outlet appears 1 year after construction. No erosion is occurring. Norm Allard is using a GNSS to check elevations in an outlet that was constructed the year before. The stream outlet is not eroding, and it's growing a diversity of aquatic plants. Here's how the primary outlet appeared 1 year after construction. Fish and woody debris that were blocked by the impoundment dam can now enter the hunting grounds when the rivers flood. A significant accomplishment of the hunting grounds ecosystem restoration project involved the removal of 1.9 kilometers of constructed dam that averaged 1.7 meters high. This photo shows a section of the dam before it was removed. The dam was dominated by reed canary grass. Orange-colored plastic ribbons were used to mark the elevation of the ground to be left after the dam was removed. A laser level and survey rod were used to guide the placement of the orange ribbons. This provided a rapid and low-cost way of guiding the excavator operators in the removal of the dam. The excavator operator used the orange plastic ribbons as a guide to create temporary benches along the inside and outside slope of the dam being removed. The orange ribbons were tied to reed canary grass above the ground that was equal to the final elevation of the dam that was being removed. The operator placed the soil on the side of the dam where there was room for spreading the soil. The temporary benches served as a visual guide, allowing the operator to rapidly remove sections of the dam that were approximately 30 meters long before we had to check elevations using the laser level. Here the excavator removes a section of the dam while the dozer pushes and spreads the soil. The excavator operator is using the benches as a guide for how much to lower the dam. We worked closely with each heavy equipment operator to show them where the soil should be spread. Heavy equipment operators are trained to place excess soil in low areas. This was a problem because the low areas on the hunting grounds were drained wetlands. We would then ask them to spread the soil on higher ground and not fill the drained wetlands. Here the soil that was in the dam has been placed in a parallel ridge by the excavator. The dozer is spreading these ridges of soil on higher ground. The dozer can do this faster and at a lower cost compared to using dump trucks or a scraper. The pieces of wood that were buried in the dam and settled on the outside of the dam are placed on the surface of the ground after the dam has been removed. The 1929 aerial photo prepared by Norm Allard was used to show the heavy equipment operators where soil could be spread without filling in the drained wetlands. We used the Avenza app on our smartphones and the 1929 aerial photo to show the operators where the historic wetlands were located so they could avoid filling them with soil. Elevations were taken regularly using the laser level as the dam was being removed. This was of critical importance as floodwater may not enter the restored wetlands and streams if high sections of the dam are left, and water could drain out of the wetlands being restored if the dam was lowered too much. The base of the wire flags shows the elevation of the dam to be removed. Norm and I were always on site supervising construction and marking the elevations for the heavy equipment operators. This photo shows a partially removed dam and some of the many holes that were found in the dam. Muskrat burrows were found in the dam being removed. These burrows were difficult to find and prevented the dam from holding water. This photo shows the foundation of the dam after a section was removed. This section of dam was built on a thick layer of organic soil. Water was leaking under the dam through this permeable organic layer. This section of the impoundment dam was built using a mixture of topsoil, silt, silty clay, and sand that was permeable. The hand shows where the dam was made using topsoil. Trees were found under the dam, also explaining why the impoundment did not hold water. I have observed that most dams built for impoundments fail to contain water because they were constructed using topsoil and were built over permeable substrates. Here the excavator is finishing the surface now that the dam has been removed. The operator loosens the soil and removes the track marks left by the heavy equipment. The rough and loosen technique is used to control erosion and to create a substrate for plant germination and growth. We could remove this dam because it was not being used as a road and the area was not being farmed. The operator shakes the bucket on the excavator to spread the loose soil over the removed dam. We shape the removed dam to restore the rim of the natural wetland. The water you see is where soil was removed years ago to build the dam. Logs were placed in the water to provide the western painted turtle with basking sites and waterfowl with loafing sites. Small ephemeral wetlands were built in places where the dam was removed. Pipes installed for the impoundment were removed as part of the restoration project. Here the drain pipe and the water control structure are being removed. The excavator operator is exposing the pipe that carried water from the pump so it can be removed. A section of the pipe that moved water from the pump is being removed. A wide and a deep trench were dug perpendicular to where each pipe passed under the dam. This allowed us to locate and to remove other pipes that had been buried in the dam. The trench was dug perpendicular to the pipes that were removed, extending down through the dam into a thick layer of clay. The trench showed where the dam had been built over topsoil and sand, explaining why the dam did not hold water. Soil high in clay was placed in the trench and compacted in layers, and this was done to prevent water from flowing along the path where the pipes had been buried in the dam. We used 2 excavators and 1 dozer to remove 1.9 kilometers of dam that was 1.6 meters high. The average width of the disturbed ground area following dam removal was 46 meters. We spread the soil on higher ground and did not fill drained wetlands. Our progress rate was 11.51 meters of dam removed per hour per machine. This means that with 1 excavator and 1 dozer working together, they removed approximately 230 meters of dam in a 10-hour day. Removing dams is not that expensive. The entire length of the dam should be removed if the objective of the project is to restore river access to a floodplain. Thick mats of dead and decaying reed canary grass, cattails, and bulrushes had filled the drained wetland basins. Norm Allard is standing in the bottom of a ditch that was dug to drain a natural wetland for construction of the impoundment. The ditch appears deep where he is standing because it is passing through the natural rim of the drained wetland. We identified all of the ditches that were dug all of the natural wetlands within the hunting grounds. The red arrow shows the location of a ditch that was dug to drain a large natural wetland in the impoundment. The large mounds were constructed within the drained wetland using soil that was removed from digging the ditch. The shoreline of the wetland before it was drained was located by the tall cottonwood trees you can see in the background. The LiDAR images we had purchased that show the hunting grounds, they were of limited value in planning the restoration. This is because of the tall reed canary grass masking the presence of ditches that were dug to drain the wetlands. This is a ditch within a ditch. The narrow ditch was dug by beaver and the bottom of a wider ditch that was dug by humans to drain the natural wetland in the impoundment. The deeper beaver channel resulted in the further drying of this wetland. We found the best way to identify drained wetlands was to examine areas on the ground. The red line shows the center of a ditch that was dug to drain a natural wetland for the impoundment. The ditch drained water into a natural stream, which was also drained. Drained streams and wetlands were best identified by the presence of tall reed canary grass, ditches, islands, and notches that were cut in the banks of streams and in the natural rims of wetlands. Colored plastic ribbons were used to show the heavy equipment operators the location of ditches to be filled and where to restore the natural rim of a wetland. The orange plastic flags show the excavator operator where to build a groundwater dam to disable the ditch that is shown by the red dashed arrow. Here the excavator operator begins the restoration of a drained wetland by removing vegetation and topsoil from the ditch to be filled. Plants and topsoil are removed from an area approximately 10 meters on either side of the ditch. The reed canary grass, its roots, and the topsoil are removed and buried. The excavator has removed the reed canary grass and topsoil from one side of the ditch to be filled. This is 2 ditches in one. Beaver have dug a narrow canal in the center of the wider ditch that was dug by humans. The next step involves building a groundwater dam at right angles to the ditch. The ditch is shown by the red arrow. The groundwater dam will control the flow of water in the soil beneath the ditch and the flow of water in the filled ditch. The groundwater dam is built where the center of the natural rim of the historic wetland was located. The pink wire flags show the operator where to begin and end digging the trench for the groundwater dam. The trench is dug deep into a dense layer of gray-colored clay. Note the roots that were severed by digging the trench for the groundwater dam. Soil that is high in clay is placed in the trench in 15-centimeter thick layers, with each layer being compacted using the bucket on the excavator. It takes time to fill the trench with clay and to compact each layer of clay. The clay used to fill the trench is obtained from the basin of the wetland that's being restored. Here the excavator operator uses the weight of the machine to compact the upper layers of clay that are placed in the trench to form the groundwater dam. The dozer shapes a naturally appearing basin and rim for the wetland while supplying the excavator with the clay soil needed to fill the ditch. It is very important that the wetland basin is dug so that it is lower in elevation than stream outlet. When the floodwater recedes, the only water remaining will be in basins that are lower elevation than the outlet. Another reason for excavating basins is to remove the thick accumulation of dead and decaying reed canary grass that has filled the drained wetlands with organics over time. People are sadly mistaken if they think that one only needs to breach the dam to restore wetlands and stream within an impoundment. Breaching a dam causes major erosion and the complete drying of the impoundment basin. The ditch is now filled and the natural rim surrounding the wetland basin has been restored. The dozer operator removes reed canary grass and soil to deepen the basin and the wetland being restored. The pile of vegetation in the basin are sedges, and these will be spread around the edge of the wetland when it's finished. The soil removed from excavating the wetland basin is spread on higher ground. We check where the soil is being spread against the 1929 aerial photo to make sure the soil is not being placed in a drained wetland. The excavator is helping the dozer move the soil so the dozer will not have to back down into the finished wetland to push the soil. The wetland has been dug deepest in the middle with gradual slopes. Compacted soils have been loosened using the rough and loosen technique. Here the dozer is shaping a low elevation inlet so that floodwater can enter and fill the wetland. The soil removed from digging the inlet is being spread on higher ground. Restored wetland basins were shaped with pits, mounds, and ridges to provide conditions for the establishment of a diversity of plants. The pits and mounds in the basins varied up to 2 meters in elevation. Cattails and reed canary grass are less likely to dominate wetlands built with pits and mounds. Excavator bucket marks were hidden and loose soil was spread in the wetland basins. We purposely loosened the soil in the wetland basin so floodwater would slowly soak into the ground and saturate the surrounding soil. The pits and mounds will provide conditions for a diversity of native plants to become established. This photo shows a natural wetland restored within the impoundment after removing the dam. The yellow flower is called bidens that was saved to provide habitat for pollinators. The roots and rhizomes of water lilies that were unearthed during construction showed that the drained wetlands and streams historically contained water. These were replanted in the restored wetlands and streams. Large woody debris was placed in restored wetlands and streams to provide the western painted turtles with basking sites, waterfowl with loafing areas, and the great blue heron with perches. The trees that were used were brought in by dump trucks. The logs were placed so they would appear natural and have naturally floated into the wetlands during a flood. The excavator operator loosened the soil and removed track marks after placing the wood. Woody debris was placed in the deeper restored wetlands to provide fish with places to hunt and to hide. The borrow pits where soil was removed to fill ditches were shaped into wetlands. This small wetland was made from a borrow pit. It's only 1 year old. This woody debris will provide fish with cover when the wetland fills. Some of the wetlands restored on the hunting grounds were made large and deep. These wetlands will contain water year-round because they are periodically inundated by floodwater from the Kootenay and the Goat River. White sturgeon and burbot, both species at risk, are being stocked in the perennial water wetlands. Some of the wetlands were restored at higher elevations so they would not be inundated by floodwater. These wetlands, called ephemeral wetlands, will dry annually. Ephemeral wetlands provide important habitat to waterfowl, amphibians, and crustaceans because they do not support fish. The restored wetlands that are not inundated by floodwater will dry by late summer. These ephemeral wetlands provide outstanding habitat for migrating ducks, geese, and swans. Many of the ephemeral wetlands that were restored will provide habitat for bidens, an important flowering plant for pollinators. Sandy loam texture soil removed during wetland restoration was placed in well-drained and sunlit locations to provide western painted turtles with nesting sites. The logs were placed to provide turtles with basking sites. Water lilies are now flourishing in the restored streams and wetlands where they had been dormant for over 50 years. The mound placed in this restored wetland is growing sedges and bidens in only 1 year. The lower elevations in the basin are growing water plankton that produces an abundance of seeds that waterfowl eat. A diversity of native plants are growing in this 2-year-old restored wetland. These aquatic plants grew naturally without seeding or planting. A diversity of aquatic plants are growing in this perennial water wetland within 1 year of restoration. 1 year ago, this drained wetland was dominated by reed canary grass. The wetland was restored by removing reed canary grass and its roots, by disabling ditches, and by restoring the depth and the contours of the natural wetland basin. We've been very successful in replacing reed canary grass with a diversity of aquatic plants. The restored wetlands are quite diverse. This restored wetland is growing burweed, rushes, and willow. Sedges dominate this restored wet meadow wetland on the hunting grounds. Sedges are important food for the elk in the fall and in the winter. One can see where elk are feeding on the sedges growing in this restored wetland. Grizzly bear tracks are commonly seen in the mud surrounding the restored wetlands. This restored wetland is growing woolgrass. This restored wetland is growing bulrushes. This photo was taken while I was standing in a section of the Goat River South that had been filled and blocked with soil to build the impoundment. The soil used for filling the river channel was obtained from digging a deep ditch to divert the Goat River South. The large amount of soil generated from digging ditches to drain wetlands was used to cut off the flow of water in a 1.15-kilometer loop of the Goat River South, and this was done to facilitate the construction of a dam for the impoundment. A 1.15-kilometer loop in the Goat River South that was cut off was reconnected by removing the 2 dams that were built to block the entrance and the exit of the loop in the river. In addition, 3 dams that were built across the cut-off channel of the Goat River South were also removed. Here we're removing one of the small dams that was built across the cut-off loop of the Goat River South. The excavator is placing a natural slope on the bank of the Goat River South after removing one of the smaller dams. Rock was used to build 2 riffles in the Goat River South. The upstream riffle directed water from the ditch section into the restored loop of the river. The downstream riffle returned water flowing from the higher elevation in the restored loop down into the ditch section of the river where the water levels were lower. Construction began by sloping the nearly vertical bank along the ditch section of the Goat River South. The excavator dug deep into the bank so the rock could be keyed in, like what is done when installing a buried vertical grade control structure. Off-road dump trucks were used to transport the rock from the storage area to the riffle site. The excavator moves and places the rock across the ditched river. The rock was also keyed into the bottom of the ditched river channel. The rock is placed in layers, with each layer being compacted using the weight of the excavator. The excavator continues to build the riffle across the ditch. More rock is added to the top and to the sides. A wedge or ramp is shaped with a gradual slope on the downstream side of the riffle. The excavator moves over to the other side of the ditch. The operator begins sloping the steep banks and then digs deep into the bank so the rock may be keyed into the bank. The rock is moved up the bank and embedded into the ground so that the water cannot flow around the rock or under the rock during a flood. The second excavator slopes the rock and packs the rock into the ground. This excavator uses soil to cover the upper portions of the rock and shapes a riverbank with gradual slopes. Personnel are in the water maintaining the silt fences and are monitoring water quality while construction is taking place. The dashed lines show the location of the upstream dam that was removed. The excavator you see in the distance is building the upstream riffle that will raise the elevation of water in the ditch so that the river will once again flow into the restored loop of the Goat River South. Water is flowing over the riffle soon after construction. You can see where gravel was placed in between and over the larger rocks to provide spawning habitat for fish. This riffle provides a way for water in the restored loop of the river to transition downslope without causing head cuts or erosion. Here's how the downstream riffle appears 1 year after construction. I've filmed this video while standing on the constructed downstream riffle. The riffle raised the elevation in the ditch section of the river by over 1 meter. Reconnecting the cutoff loop of the Goat River South helped to restore groundwater elevations in the hunting grounds. The restored loop of the Goat River South is now providing habitat to the western painted turtle, the white sturgeon, and the burbot. Numerous large mounds of soil were formed across the landscape of the hunting grounds. These were built to provide nesting sites for waterfowl. The impoundments surrounding each nesting island remained dry because the dam for the impoundment did not hold water, and the natural wetlands had been drained as part of impoundment construction. Here's an example of the mounds that were built using the soil removed from digging ditches to drain 2 of the natural wetlands. The ditches were hard to find because they were dug wide and shallow, unlike ditches dug to drain land for farming. This aerial photo shows the same drained wetlands we restored 1 year after construction. This was done by leveling the mounds, filling the ditches, and reshaping the wetland basins. The yellow flower, named bidens, is growing in a moat surrounding a mound. The moat is connected to ditches that were dug to drain the natural wetlands. Aquatic plants are growing in the moat because the soil was removed to make the mound. This massive mound was built with a natural abandoned river channel wetland. The mound blocked water from entering the river channel. This large mound prevented water from flowing into or out of the abandoned river channel. Here the dozer operator removes the large mound of soil. The soil from the mound was used to fill drainage ditches and to restore the rims of natural wetlands that had been drained. Care was taken not to fill historic wetlands with soil that was removed from leveling the islands. The 1929 aerial photo proved to be invaluable in quickly identifying where historic wetlands were located. Dwight Evans, the skilled individual operating the Caterpillar D6R LGP dozer, was able to remove an average of 2 large islands in a 10-hour day. Here's how the abandoned river channel appears 1 year after the mounds were removed and the ditches were filled. Dwight Evans was able to remove the smaller mounds in 1 hour or less. This included the time needed to restore small wetlands of various types in the same locations. Ephemeral streams were restored following the removal of many of the smaller mounds. Wetlands were often built after the islands or mounds were removed. This was one of the many small wetlands restored where a mound was located and removed. Wet meadow wetlands were formed by shaping shallow depressions on the locations where the mounds were removed. A diversity of aquatic plants is growing where the large mound of soil was removed. The sedges provide grizzly bears and elk with food. This wet meadow wetland was restored following the removal of a nesting island. Here's another river channel that we restored. I sincerely thank Norm Allard and the Yaqan Nukiy First Nations for making this project possible. Our total cost for engineering design and for permitting was less than 3% of the total budget for the project. The Hunting Grounds Ecosystem Restoration Project was a success. In the spring of 2022, floodwater inundated the restored wetlands, streams, and rivers. The project reconnected over 519 acres of floodplain containing restored wetlands and streams with the Kootenay River, the Goat River, and the Goat River South. The project showed that artificial impoundments may be restored to a diversity of naturally appearing and functioning wetlands, streams, and rivers that will provide habitat for waterfowl and for species at risk. Wetlands of all different sizes and types were restored in the same locations where they were found before the impoundment was built. You can see how the wetlands are hydrologically connected. The dams that prevented floodwater from entering the hunting grounds were removed. The natural rims of wetlands that were drained with ditches were restored. The wetland basins were deepened so that water would remain after a flood. If you look closely, you can see the small wetlands that were restored on the same sites where the large mounds of soil were removed. Willow trees are once again growing around the wetlands and not in the dry basins. Many people think that you only need to breach a dam to reconnect an impoundment with floodwater. They are wrong. One must purposely design and build inlets that carry water onto the floodplain, excavate basins that will hold the water after a flood, and then construct outlet streams that won't erode when the floodwater recedes. The drone is now flying over the inlet stream we built to connect the Goat River with the hunting grounds. You can see how the muddy water in the Goat River is entering the inlet stream and then flowing into the restored wetlands. You're looking at a natural ecosystem that has been restored with no dams, pipes, water control structures, pumps, or diversions. The Hunting Grounds Ecosystem Restoration Project was a partnership that involved the Yaqan First Nations, the Fish and Wildlife Compensation Program, the Columbia Basin Trust, and the BC Wildlife Federation. This project accomplished a great deal. It restored wetlands, streams, and rivers that were impacted by the construction of a large impoundment years ago. Now, these techniques that we developed in doing this project are applicable in restoring wetlands, streams, and rivers in impoundments across North America. Well, if you liked this video, please let us know that you liked it and subscribe so you won't miss any future episodes. And I wish you every success getting out there, designing and restoring wetlands and streams. Thank you.